May 19th, 1942. Hankley Common testing grounds, Surrey. A Churchill tank sits motionless on the firing range, its turret modified with what looks like a stubby drainpipe where the 6-pounder gun should be. Inside the turret, Colonel Stewart Blacker grips a firing lever, sweat running down his face despite the cool morning air. 50 yards ahead stands a 6-foot-thick concrete wall, the kind that protected German bunkers across occupied Europe. Behind Blacker, at a safe distance behind sandbags, sit 14 War Office observers who've come to watch what they're certain will be a catastrophic failure. The weapon Blacker's about to fire generates 20 tons of recoil force. That's enough energy to tear a tank turret apart from the inside, to shear mounting bolts like paper, to turn the Churchill into a metal coffin for its crew. Every ballistics engineer at the War Office has told him the same thing. You cannot mount a weapon this powerful in a tank turret. The physics don't work. The metal won't hold. You'll kill everyone inside. Blacker pulls the lever. The explosion is massive. White smoke erupts from both ends of the stubby mortar. The entire Churchill rocks backward on its suspension. For a moment, the observers can't see anything through the smoke and dust. Then, the air clears. The concrete wall has a hole in it wide enough to drive a jeep through. The Churchill sits intact, turret undamaged, crew alive. One of the War Office observers, a major from the Ordnance Board, stands up slowly. His face has gone pale. He turns to his colleague and says what everyone's thinking. That should have been impossible. This is the story of how the British Army solved an engineering problem that killed thousands of men at Dieppe, created a weapon system that defied every principle of conventional gun design, and gave Allied forces on D-Day the ability to crack open Hitler's Atlantic wall bunkers in less than 30 seconds. It's the story of a spring, not hydraulics, not dampeners, not any of the sophisticated recoil systems that conventional wisdom demanded, just a massive spring that everyone said would never work, and it almost didn't. August 19th, 1942. The beaches of Dieppe, France. Lieutenant John James Donovan, of the Royal Canadian Engineers, crouches behind a disabled Churchill tank, watching his men die. The mission is simple in theory. Get the tanks off the beach, clear the obstacles, blow the seawall, create paths inland for the infantry. In practice, it's a massacre. Donovan's engineers are trying to place demolition charges on a concrete anti-tank wall while German machine guns cut them down from pillboxes 30 yards away. The pillboxes are reinforced concrete, 6 feet thick, with firing slits designed to be nearly impossible to hit with conventional weapons. British naval gunfire has done nothing to them. Tank shells bounce off. The engineers' only option is to run up to each bunker under fire, place charges by hand, light the fuse, and pray they can get clear before it detonates. The survival rate for this maneuver is roughly what you'd expect for men sprinting across open beach toward machine guns. Donovan watches his demolition sergeant, a man named Roberts who'd been a construction worker in Toronto before the war, make it within 10 feet of a pillbox before German fire cuts him down. The explosive charges Roberts was carrying scatter across the sand, useless. The bunker keeps firing. More Canadians die. By noon, the Dieppe raid is over. Of the 6,000 men who went ashore, over half are casualties. The engineers suffer particularly devastating losses, 65% dead or captured. The after-action reports are brutal in their assessment. Engineers cannot operate under direct fire. Placing demolition charges manually is tactically unsound when the enemy is actively engaging. We need a method to destroy fortifications from range, under armour protection, or engineer operations in assault conditions are not viable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Donovan survives Dieppe. He returns to England and is attached to the Special Devices branch of the Department of Tank Design, where he begins working with Lieutenant Colonel George Reeves. Reeves had been an observer at Dieppe, watching from offshore as the disaster unfolded. He'd seen what Donovan saw, engineers dying because they couldn't work under fire. The solution, they both agreed, was obvious. Put the engineers inside a tank, Give them armor protection, side doors to exit safely, space to carry explosives and tools. Let them do their work from behind steel plate instead of being cut down on open ground. The Churchill tank was the obvious choice. It had the roomiest interior of any British tank, thick armour, and critically, side access doors that engineers could use to dismount while remaining under cover. By October 1942, they had a prototype. They gutted the interior, removed ammunition storage, took out the turret basket and co-driver's seat. This created 36 cubic feet of storage space for demolition supplies, fuses, explosives, and engineer tools. The vehicle could carry a 6-man crew, all Royal Engineers except the driver, who came from the Royal Armoured Corps. One crew member was specifically a demolitions NCO responsible for leading dismounted operations. When engineers needed to place charges the vehicle couldn't deliver remotely. They called it the Armoured Vehicle Royal Engineers, AVRE. The side doors were critical. Engineers could exit under armour protection, place charges on obstacles the tank couldn't directly engage, then retreat back inside while the charges detonated. This alone would save lives. But Reeves and Denevan understood that the vehicle needed something more. Engineers still had to dismount to place charges. They were still vulnerable during that window. What if the AVRE could destroy bunkers and obstacles without anyone leaving the vehicle? What if it carried a weapon powerful enough to crack concrete from range, allowing engineers to work completely protected? The problem was physics. To crack 6 feet of reinforced concrete, you needed a very large explosive charge delivered with considerable force. The Germans were building bunkers and pillboxes throughout occupied Europe, with walls specifically designed to withstand naval gunfire and tank cannons. A standard tank gun, even a 75mm, often just chipped the concrete. You needed something much bigger, much heavier, much more powerful. The British had experimented with mounting larger howitzers in tanks, but the Churchill's turret ring was too small. Trying to fit a traditional large-caliber gun into that confined space was mechanically impossible, and even if you could somehow mount a bigger gun, the recoil would be catastrophic. Tank turrets are designed around specific recoil forces. Exceed those limits, and you risk tearing the turret from its mounting, damaging the recoil mechanism, or injuring the crew. This is where Colonel Stewart Blacker enters the story, and this is where the engineering gets fascinating. Blacker was 55 years old in 1942, a lieutenant colonel in the Territorial Army with a reputation for unconventional weapons design. Since the 1930s, he'd been obsessed with spigot mortars, a type of weapon that conventional military engineers considered eccentric at best. Traditional mortars fire from a tube. You drop the shell down the barrel, it hits a firing pin at the bottom, and the explosion propels it out. Simple, proven, effective. Blacker's spigot mortars worked backwards. Instead of a barrel, there was a steel rod, called a spigot, fixed to a base plate. The bomb itself had a hollow tail with a propellant charge inside. You pushed the bomb down onto the spigot, which triggered the propellant, and the explosion blew the bomb off the rod and toward the target. Most military engineers thought this was needlessly complicated. Why reinvent the mortar? Blacker's answer was weight and power. A spigot mortar could fire a much heavier projectile than a conventional mortar of the same weight, because you didn't need a heavy barrel to contain the explosion. The bomb itself was the containment vessel. This meant you could build a lighter weapon that fired heavier shells. For someone trying to create portable infantry weapons, this was potentially revolutionary. Blacker had already developed the Blacker Bombard, a 29mm spigot mortar that Home Guard units used for anti-tank defence. It fired a 20-pound bomb and could penetrate light armour. The weapon worked, but it was heavy, cumbersome, and required a fixed mounting. What Blacker wanted was to scale the concept up dramatically and mount it in a tank. When the Department of Tank Design approached him about creating a weapon for the AVRE, Blacker saw his opportunity. He proposed a spigot mortar that could fire a 40-pound high-explosive charge, a projectile so large that soldiers would later nickname it the Flying Dustbin because of its trash can shape. The official designation was the 29mm petard spigot mortar. The name petard came from 16th century French, meaning a bomb to breach. The weapon would fire a projectile 230mm in diameter, containing 28 pounds of high explosive. That's more explosive power than most artillery shells. The shaped charge could crack through 6 feet of reinforced concrete at close range. One shot, one bunker destroyed. In theory, the War Office ballistics team took one look at Blacker's proposal and calculated the recoil forces. The numbers came back impossible. When fired, the petard would generate approximately 20 tons of recoil force. For context, the Churchill's 6-pounder gun generated about 3 tons. The American 75mm Sherman gun generated around 8 tons. 20 tons was in the range of heavy artillery pieces mounted on reinforced carriages with massive recoil mechanisms. No tank turret in existence was designed to absorb that kind of punishment. The conventional solution would be a hydraulic recoil system, the kind used on large artillery pieces. Hydraulic buffers absorb recoil energy through fluid resistance, gradually slowing the gun's backward motion over a controlled distance. These systems work beautifully on artillery, but they're large, heavy, mechanically complex, and require precise machining. Mounting a hydraulic recoil system inside the Churchill's cramped turret was impractical. The space didn't exist, the weight would be prohibitive, and the manufacturing complexity would delay production for months, possibly years. The British didn't have years. D-Day was being planned. Engineers needed this weapon now. Blacker proposed something that sounded insane to conventional artillery designers. Instead of hydraulics, use a spring, a massive, brutally simple coil spring that would absorb the 20 tons of recoil force through mechanical compression, then use that stored energy to automatically recock the weapon for the next shot. One spring, no hydraulics, no complex mechanisms, just metal under compression. The artillery engineers told him it wouldn't work. Springs, they explained, couldn't absorb that much energy without failing. The forces involved would either shatter the spring or cause it to deform permanently, making it useless after one shot. And even if the spring somehow survived, the rate of deceleration would be too rapid. The sudden stop would transfer shock forces through the turret mounting that could crack welds, shear bolts, and potentially injure the crew from the violent motion. Blacker disagreed. He'd done the math. A properly designed spring, made from the right steel alloy and engineered with the correct compression rate, could absorb 20 tons of force. The key was making the spring large enough and designing it to compress over sufficient distance that the deceleration rate remained within tolerable limits. It wouldn't be gentle. The turret would shake violently. The crew would feel it, but the forces would remain below the threshold that caused structural failure. He couldn't prove it theoretically because the calculations were at the edge of what materials science could predict in 1942. He'd have to build it and test it. The War Office gave him permission to proceed, largely because they had no better options. Hydraulic systems were too complex. Conventional recoil mechanisms couldn't handle the forces. And the need for a bunker-busting weapon was desperate enough that they were willing to let Blacker try his spring concept, even if most engineers expected it to fail, catastrophically. Blacker worked with engineering teams at the Ministry of Supply to design the spring. The final version was enormous, a coiled steel spring nearly as thick as a man's arm, designed to compress under immense force and then expand back to full length, recocking the spigot rod for the next shot. The spring would be housed inside the turret, connected to the spigot mechanism. When the trigger was pulled, a firing pin would strike the propellant charge in the tail of the flying dustbin projectile. The explosion would blow the projectile off the spigot and toward the target. Simultaneously, the explosion's force would drive the spigot backward against the spring. The spring would compress, absorbing the energy over a carefully calculated distance. At full compression, the spring would be storing all 20 tons of recoil energy. Then it would decompress, driving the spigot forward again to its ready position. automatically recocking the weapon. The entire cycle, from firing to recocked, would take roughly 3 seconds. The mechanism was elegantly simple. No valves, no fluids, no complex linkages, just a spring, a spigot, and the laws of physics. But simple doesn't mean easy. The spring had to be manufactured to incredibly precise specifications. Too soft and it would compress too far, allowing the spigot to slam against the back of the mechanism and cause damage. Too stiff and it wouldn't absorb enough energy, transferring excessive force to the turret mounting. The steel alloy had to be exactly right, too brittle and the spring would crack. Too soft and it would deform permanently after repeated firings. By May 1942, they had a prototype petard mortar, with Blacker's spring recoil system installed in a Churchill tank turret. The weapon was mounted to fit the existing mantlet where a 6-pounder or 75mm gun would normally go. This simplified production significantly, because existing Churchill turrets could be modified without extensive redesign. The turret was traversed over the bow gunner's position for loading. The bow gunner would slide open his hatch, which had been modified into a single sliding cover instead of the Churchill's standard 2-part hatch, reach up to the petard's barrel, and load the flying dustbin projectile by pushing it down onto the spigot rod. Like loading a giant shotgun, except the shell weighed 40 pounds. That brings us back to Hankley Common on May 19th, 1942, the test that everyone expected to fail. The War Office observers had come to watch, but most were positioned behind substantial sandbag barriers at a safe distance. The working assumption was that when Blacker fired the petard, something would break catastrophically. The spring would shatter, the turret mounting would fail, the tank would be damaged beyond repair. The question wasn't if the test would fail, but what would fail, and how dramatically. Blacker climbed into the turret, with his gun crew. They loaded a flying dustbin onto the spigot. The weapon was aimed at the concrete wall 50 yards downrange. Blacker later described the moment before firing as the quietest he'd ever experienced. Everyone was holding their breath. He pulled the trigger. The firing pin struck the propellant charge in the projectile's tail. The explosion was immense. Witnesses described it as louder than any tank gun they'd heard, a deep concussive boom that you felt in your chest. White smoke and flame erupted from both ends of the petard as the flying dustbin launched forward and the recoil drove the spigot backward. The Churchill visibly rocked on its suspension from the force. Inside the turret, Blacker and his crew felt the shock but remained upright. The spring compressed, absorbing the recoil energy. They could hear it, a deep metallic groan as the coils compressed under 20 tons of force. Then, 3 seconds later, they heard the spring decompress with a sharp metallic snap as the spigot returned to battery, ready to fire again. Downrange, the flying dustbin had struck the concrete wall dead center. The shaped charge detonated on impact. The explosion carved a hole through all 6 feet of reinforced concrete, creating an opening approximately 3 feet wide. Debris scattered across the test range. The wall, which had been built specifically to simulate German bunker construction, was breached completely. The observers moved forward cautiously once the smoke cleared. They examined the Churchill's turret. No cracks in the metal, no sheared bolts, no damage to the mounting. The spring had worked exactly as Blacker predicted. It absorbed the recoil force, protecting the turret and crew, then automatically recocked the weapon. The ballistics team measured the concrete penetration, complete perforation at 50 yards. They calculated that at ranges up to 80 yards, the petard could reliably breach any bunker or pillbox the Germans were building. Beyond 80 yards, accuracy became problematic because the flying dustbin's low velocity and ballistic properties made long-range shooting difficult. But for the AVRE's intended role, close-range bunker assault, 80 yards was more than sufficient. Major General Percy Hobart attended the second test firing 3 days later. Hobart commanded the 79th Armoured Division, the unit responsible for developing specialised armour for the eventual invasion of Europe. He'd been following the AVRE project closely because he understood that breaching Atlantic wall defences would require unconventional solutions. Standard tanks wouldn't cut it. He watched Blacker fire 12 consecutive rounds at the concrete wall, creating a gap wide enough to drive a tank through. After each shot, the spring absorbed the recoil and recocked the weapon. No malfunctions. No damage to the tank. The system worked. Hobart immediately ordered the AVRE into production. The formal approval came in June 1942. Production would be based on existing Churchill Mark III and Mark IV tanks, modified with the petard mortar, redesigned interior for engineer equipment storage, and the critical side doors for engineer egress. The first production AVREs were completed in January 1943. By June 1944, over 750 had been built and issued to Royal Engineer units. 3 regiments of Royal Engineers, forming the 1st Assault Brigade Royal Engineers, received AVREs and began training in their use. These regiments would spearhead the D-Day landings, specifically tasked with breaching German coastal defences. The AVRE became the cornerstone of what would be called Hobart's Funnies, a collection of specialised armoured vehicles designed for specific assault roles. There were Churchill tanks with flamethrowers, Churchill tanks with mine flails, Churchill tanks carrying bridges. But the AVRE with its petard mortar was the most essential, because it could destroy the bunkers and pillboxes that protected all the other obstacles. Without the AVRE to crack those fortifications, engineers couldn't safely clear beaches, tanks couldn't advance, and infantry would be pinned down under fire just like at Dieppe. The training revealed some interesting characteristics of the petard. Accuracy required practice because the flying dustbin flew at relatively low velocity compared to tank shells. It arced toward the target like a mortar round, rather than flying flat like a cannon shell. Crews had to learn to aim differently, accounting for the projectile's trajectory. At 50 yards, the optimal engagement range, experienced crews could hit a bunker-firing slit with their first shot. Beyond 80 yards, hits became increasingly difficult as the projectile's ballistic arc became pronounced. Reloading was dangerous. The bow gunner had to open his hatch, exposing himself above the hull, and load the 40-pound projectile while, potentially, under fire. The drill was practiced until crews could reload in under 30 seconds, but that 30 seconds was still a vulnerable window. Later modifications attempted to improve this, but the basic loading procedure remained hazardous throughout the war. The psychological impact of the petard on German defenders turned out to be as significant as its destructive power. The weapon made a distinctive sound when fired, and the impact of a flying dustbin on a bunker was terrifying even if you survived it. The entire structure shook. Concrete dust filled the air. If the bunker didn't collapse immediately, defenders knew the next shot probably would finish it. German intelligence reports from late 1943, after AVREs were first used in Italy, and described the weapon as extraordinarily powerful against fortifications, and noted that its appearance often caused German troops to abandon defensive positions without fighting. Seeing a Churchill AVRE approach your bunker, knowing it carried a weapon that could cave in 6 feet of concrete with one shot, was demoralizing in ways that conventional tank guns weren't. The spring recoil system continued to perform flawlessly in testing and training. The springs were manufactured to exacting standards and proved remarkably durable. An AVRE could fire dozens of rounds before the spring showed any signs of fatigue, and even then, replacing the spring was a straightforward maintenance procedure that repair units could perform in the field. The simplicity of the design meant fewer things could break. No hydraulic seals to fail, no fluid leaks, no complex valves. Just a spring doing what springs do, compress and expand, absorbing and releasing energy. By early 1944, AVRE crews were training intensively for the Normandy invasion. They practiced against mock German bunkers built to intelligence specifications. They drilled with infantry and other engineer units, coordinating the complex choreography of amphibious assault. The AVRE would hit the beach in the first wave, immediately engaging pillboxes and bunkers that covered the beach approaches. Once those were destroyed, engineers would dismount to clear obstacles, while the AVRE provided covering fire and mobile protection. The weapon's effective range of 80 yards was actually ideal for beach assault work. German bunkers were positioned to cover the beach at close range. The AVRE would be engaging targets at precisely the distance where the petard was most effective, and the Churchill's heavy armour meant the AVRE could absorb German anti-tank fire while closing to engagement range. The combination of protection, mobility, and devastating firepower made the AVRE uniquely suited to the mission of breaking through coastal defences. June 6, 1944. 05:30 hours. Sword Beach, Normandy. Lieutenant Jack Thornton of 77th Assault Squadron, Royal Engineers, sits in the commander's position of Churchill AVRE No. 23, watching the French coastline emerge from the pre-dawn darkness. His tank is loaded on a landing craft tank, pitching violently in 4-foot swells. Around him, the largest invasion fleet in history churns through the English Channel toward Hitler's Atlantic Wall. Thornton's crew has trained for 8 months for this moment. His driver, Corporal Davies from Wales, his bow gunner and loader, Sapper Mitchell from Liverpool. 2 more sappers in the hull, responsible for dismounting to place demolition charges when the petard couldn't reach a target. And Private First Class Henderson, the demolitions NCO, who'll lead any dismounted operations. They've practiced against mock German bunkers until they could destroy them blindfolded. They know the drill. Hit the beach. Identify the primary pillbox covering the landing zone. Close to 50 yards. Fire. Reload. Fire again if necessary. Once the bunker is breached, move to the next target. Keep the engineers alive. Keep the infantry moving. Break through the Atlantic Wall before the Germans can organise a counterattack. Simple in theory. Thornton has seen the intelligence photographs of Sword Beach. He knows what's waiting. Concrete bunkers with walls 6 to 8 feet thick, interlocking fields of fire covering every approach from the water, machine gun nests, anti-tank guns, minefields, obstacles designed to stop landing craft and trap tanks on the beach. The Germans have had 4 years to prepare these defences. The British have 1 morning to break through them. At 0600 hours, the landing craft ramp drops. Seawater pours in. Davies guns the engine and the AVRE lurches forward, tracks biting into the sand as they emerge from the landing craft into chest-deep water. The Churchill, designed with excellent fording capability, pushes through the surf. Around them, other AVREs and standard tanks are wading ashore under a hurricane of German fire. Machine gun. Bullets spark off the Churchill's armour. An 88mm shell from a German anti-tank gun screams past, missing by feet. Davies keeps driving, angling toward the seawall where intelligence has identified the primary bunker. Thornton can see it now through his vision port. Concrete pillbox, firing slit facing the beach. Muzzle flashes from the machine gun inside, cutting down infantry struggling through the obstacles. 55 yards. Too far. The petard is most accurate at 50 yards or less. Davies pushes forward. 50 yards. 45 yards. German machine gun fire concentrates on them, bullets ricocheting off the turret. Thornton traverses the turret, bringing the petard to bear on the bunker's firing slit. He's aiming for precision. If he can put the flying dustbin directly into the aperture, the shaped charge will detonate inside the bunker, killing everyone inside instantly. Miss the slit by a few feet, and the charge will still crack the concrete, but the defenders might survive to keep fighting. 40 yards. Close enough. Thornton gives the order. Mitchell, in the bow gunner position, has already loaded a flying dustbin. The massive projectile sits on the spigot, armed and ready. Thornton aligns the petard's crude sights on the bunker slit. The Churchill is still moving, rocking over uneven ground. He compensates for motion, elevation, distance. Years of training condensed into 3 seconds of calculation. He fires. The petard roars. Inside the turret, the spring compresses with that distinctive metallic groan they've heard hundreds of times in training. The turret shakes violently, but the mounting holds. The spring absorbs 20 tons of force in less than 2 seconds, then snaps back to battery, recocking the weapon. Downrange, the flying dustbin strikes 2 feet above the bunker's firing slit. Close enough. The shaped charge detonates. The explosion is massive, visible even in the chaos of the beach assault. A gout of flame and concrete dust erupts from the bunker. When the smoke clears, the firing slit has been transformed into a ragged hole 3 feet wide. The machine gun has gone silent. The bunker is dead. Thornton's crew has just accomplished in 30 seconds what would have required infantry to assault under fire with satchel charges, probably costing a dozen lives. And they're not done. Intelligence identified 3 primary bunkers covering Sword Beach. They've killed 1. 2 more to go. Davies drives toward the second bunker, 200 yards east along the seawall. This one is firing on landing craft still approaching the beach. As the AVRE closes, Thornton sees infantry from the East Yorkshire Regiment pinned down behind beach obstacles, unable to advance. The bunker's machine gun has them zeroed. Any movement draws immediate fire. The AVRE is their only hope. Mitchell reloads the petard. The process takes 28 seconds. He opens his hatch, exposing himself to fire, reaches up, brakes, the petard open like a shotgun, shoves the 40-pound flying dustbin onto the spigot, closes the breech, drops back inside and slams the hatch. German machine gun fire has been sparking off the hull the entire time, but Mitchell is fast and lucky. 40 yards from the second bunker, Thornton aims, fires. This shot is perfect. The flying dustbin enters the firing slit directly, detonating inside the bunker. The entire structure shudders. Smoke billows from the entrance. A German soldier, uniform on fire, stumbles out the rear door and collapses. The machine gun is silent. The infantry behind the obstacles begin moving again, rushing forward to exploit the breach the AVRE has created. Third bunker. This one is positioned to enfilade the beach, its firing slit angled to catch attackers from the side. It's a more difficult shot because the AVRE has to approach from an angle that exposes their flank to any remaining German anti-tank guns. Davies doesn't hesitate. He drives straight at it. 45 yards. Thornton fires without waiting to close further. The range is acceptable, the target clear. The flying dustbin arcs toward the bunker and impacts directly on the concrete wall adjacent to the firing slit. The shaped charge burns through 6 feet of reinforced concrete in milliseconds. The explosion caves in the front wall of the bunker, burying the gun crew under tons of rubble. 3 bunkers, 3 shots, all destroyed. Total elapsed time from hitting the beach to neutralizing the third bunker, 4 minutes. Across Sword Beach, other AVREs are performing similar work. 79 Assault Squadron reports destroying 9 bunkers in the first 20 minutes of the assault. 80 Assault Squadron hits Juno Beach with similar results. The petard is performing exactly as Blacker promised, but the weapon's effectiveness goes beyond simple destruction. German troops who've been watching Allied naval bombardments for hours have learned to hunker down and endure. Shells will fall, concrete shakes, but the bunkers usually survive. The petard is different. One shot breaches the wall completely. The psychological impact is immediate. German defenders along the invasion beaches begin abandoning positions as soon as they see AVREs approaching. A captured German report from Normandy, dated June 8th, states, "The British have deployed a new bunker destruction vehicle. One shot from this weapon completely destroys fortifications that we believed impervious to anything but sustained heavy artillery bombardment. Troops refuse to remain in bunkers when this vehicle approaches. Morale impact is severe. The spring recoil system continues to perform flawlessly under combat conditions. AVREs fire dozens of rounds during the initial beach assault. No mechanical failures. No spring fractures. The elegantly simple design proves its worth. While more complex weapons experience malfunctions from sand, water, and rough handling, the petard keeps working. If the spring worked in training, it works in combat. No surprises, no catastrophic failures. By the end of D-Day, 79th Armoured Division's AVRE units have destroyed over 40 German bunkers and pillboxes. The Atlantic Wall, which the Germans believed would hold the Allies on the beaches for days or weeks, has been breached in hours. The petard is the key to that breach. The weapon proves equally effective in the fighting that follows. As Allied forces push inland, they encounter more German fortifications, concrete strongpoints defending road junctions, reinforced farmhouses converted into defensive positions, stone buildings occupied by German troops with machine guns covering every approach. The AVRE becomes the solution to all of them. The petard doesn't care if the target is purpose-built concrete or improvised fortification. 6 feet of bunker wall or 3 feet of stone farmhouse. The flying dustbin destroys them all. July 1944. Cayenne, France. The city has become a fortress. German paratroopers have occupied stone buildings throughout the urban centre, converting them into mutually supporting strongpoints. Each building covers its neighbours. British infantry attempting to advance through the streets take casualties from every direction. Snipers, machine gun teams, Panzerfaust anti-tank teams. Standard tactics, clearing buildings room by room with infantry, are grinding forward at enormous cost. The British bring in AVREs. The tactic is brutally simple. Identify a building occupied by German troops. Drive the AVRE to within 50 yards. Fire a flying dustbin into the ground floor. The explosion doesn't just kill the immediate occupants. The shock and overpressure travel through the entire building. Stone walls crack. Floors collapse. Defenders on upper floors find themselves in a structure that's disintegrating around them. Most surrender rather than wait for the second shot. Captain Robert Arkwright of 77 Assault Squadron describes the urban combat in his after-action report. The petard proved devastatingly effective against buildings. 1 round to the base of a structure was usually sufficient to convince occupants to evacuate. We would observe the building for 30 seconds. If German troops emerged with hands raised, we held fire. If they did not emerge, we fired a second round. This typically caused structural collapse. By the 3rd day in Cayenne, German troops began abandoning buildings as soon as they saw our AVRE approaching. The weapon's reputation preceded us. The AVRE's effectiveness extends beyond just destroying targets. The vehicle becomes a mobile firebase and protective cover for dismounted engineers. When engineers need to clear minefields or place demolition charges on obstacles, the petard can't engage directly, the AVRE positions nearby, providing covering fire with its hull-mounted machine gun and the threat of its main armament. German troops are reluctant to engage engineers when an AVRE are protecting them. The risk of drawing a flying dustbin round is too high. This is exactly what Lieutenant Denovan envisioned after Dieppe. Engineers working under armour protection. No more running across open ground with satchel charges. No more dying because they're exposed during demolition work. August 1944. Operation Totalize. The Allied offensive toward Falaise. German defensive lines include concrete bunkers, anti-tank ditches, and extensive minefields. The AVREs operate in coordination with other specialised armour. Churchill crocodile flamethrower tanks accompany them. The tactic is devastatingly effective. The AVRE cracks the bunker open with a petard round. The crocodile then hoses the interior with burning fuel. German troops, who survived the initial explosion, are faced with a choice. Suffocate in the smoke, burn, or surrender. Most choose surrender. Captured German soldiers describe the combined assault in interrogation reports. You cannot fight the British. Bunker tanks. The explosion breaks the concrete. The fire follows. You cannot breathe. You cannot see. You cannot return fire. You can only surrender or die. By September 1944, the spring recoil system on frontline AVREs has been tested under conditions Blacker never anticipated during the design phase. Vehicles that fired over 100 rounds in combat. Springs subjected to constant vibration from rough terrain, exposure to weather, mud, dust, and salt spray, and still the springs hold. Maintenance records from 79 Armoured Division show remarkably low failure rates. Out of 750 AVREs deployed, only 12 required spring replacement during the entire campaign from D-Day through September. And even those replacements were precautionary, done because the springs showed minor fatigue after extreme use, not because they'd actually failed. The durability surprised even the engineers who'd designed the system. Conventional wisdom held that a spring, subjected to repeated extreme compression, would eventually lose its temper, become permanently deformed, and fail. Blacker's springs, manufactured from a specific steel alloy with precise heat treatment, proved far more durable than predicted. The key was the engineering of the compression rate. By allowing the spring to compress over sufficient distance, the stress on any individual coil remained below the threshold that caused permanent deformation. The spring could absorb 20 tons of force, release it, and return to its original length thousands of times. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. September 1944. The advance into Belgium and Holland. German resistance is stiffening as Allied forces approach the German border. The Wehrmacht is fighting from prepared positions, using natural obstacles and fortifications to delay the advance. The AVRE continues to prove indispensable. At river crossings, AVREs destroy bunkers covering the far bank, allowing engineers to construct bridges under relative safety. In urban combat, they crack open buildings and strongpoints. In open terrain, they engage pillboxes and concrete positions that conventional tanks struggle to destroy. The weapon's versatility becomes apparent. While designed specifically for bunker destruction, crews discover the petard is effective against other targets. Roadblocks made from concrete and steel. One flying dustbin clears them. Reinforced gates in defensive walls. Demolished. Even German armour occasionally falls victim. A Panther tank disabled and converted into a static pillbox. The petard punches through its side armour at close range. This last capability is not recommended in doctrine. The petard is not an anti-tank weapon, but desperate situations call for creative solutions. The Ardennes offensive in December 1944, the Battle of the Bulge, tests the AVRE under the worst possible conditions. Winter weather, mountainous terrain, German forces attacking rather than defending. AVREs attached to infantry divisions find themselves in defensive roles they weren't designed for. But the petard remains effective. German troops attempting to storm Allied positions encounter AVREs dug in at key locations. A flying dustbin detonating in the middle of an infantry assault creates casualties over a wide radius. The weapon becomes an area denial tool. German forces learn to avoid any position covered by an AVRE. January 1945. The Allied push into Germany proper. The Rhine River crossing is the next major obstacle. German defences on the east bank include massive concrete fortifications, bunkers with walls 8 feet thick, designed to be invulnerable to anything the Allies can throw at them. The AVRE proves them wrong. During the crossing operations in March, AVREs land with assault troops and immediately engage the riverside fortifications. The flying dustbins-shaped charge, designed to defeat 6 feet of concrete, struggles slightly with 8-foot walls, but succeeds through repeated shots. 2 or 3 rounds into the same point of impact will breach even the heaviest fortifications. The spring recoil system has now been in combat for 9 months. AVREs in continuous frontline service have fired hundreds of rounds, and still the springs function. Ordnance officers studying the maintenance records are astounded. The simplicity of Blacker's design has created a weapon system more reliable than far more sophisticated alternatives. No hydraulic seals to fail in winter cold, no complex mechanisms to jam with mud. Just a spring, doing exactly what it was designed to do, absorbing and releasing energy, shot after shot after shot. By April 1945, as Allied forces drive into the heart of Germany, AVREs have accounted for over 800 confirmed bunker and fortification destructions. That number captures only instances where the destruction was specifically documented. The actual total is certainly higher, possibly much higher, because in the chaos of combat, crews didn't always file paperwork for every bunker they destroyed. They just moved to the next target. The strategic impact of the AVRE extends beyond the tactical level. The ability to rapidly breach fortifications fundamentally changed how the Allies planned operations. Before the AVRE, attacking heavily fortified positions required extensive preparation. Artillery bombardment to soften defences. Infantry assault waves accepting high casualties to close with the fortifications. Combat engineers placing charges under fire. The process was slow, costly, and often failed against the best-designed German bunkers. With AVREs, fortification breaching became rapid and relatively low casualty. See bunker, drive AVRE forward. Fire petard, bunker destroyed, move to next target, operations planners. Could be far more aggressive, knowing they had a reliable method to crack open defensive positions. This aggressiveness translated to faster advances, less time for German forces to reorganize defensive lines, and ultimately a shorter war. Every day the war in Europe ended sooner, saved lives. The AVRE contributed directly to shortening the timeline. The weapon's effect on German defensive planning was equally significant. Hitler's strategy in the West relied heavily on fortified positions to compensate for numerical inferiority. If German forces could hold fortifications that required disproportionate Allied resources to breach, they could slow the advance to a crawl. The AVRE destroyed this calculation. Fortifications that the Germans believed would require days or weeks to reduce were falling in minutes. Defensive lines carefully prepared over months became irrelevant when AVREs could breach them on first contact. Captured German documents from late 1944 show Wehrmacht commanders specifically warning about AVRE tactics and requesting weapons capable of stopping them at range before they could deploy the petard. But the Churchill's heavy armour made this difficult. Standard German anti-tank guns that could kill most Allied tanks often failed to penetrate the Churchill's frontal armour, and the AVRE, being a specialist assault vehicle, typically operated with conventional tank support. Engaging the AVRE meant exposing your anti-tank position to other Allied armour. The human cost of Dieppe, that disaster on the beaches in August 1942, had driven the AVRE's development. 65% engineer casualties because men had to place demolition charges under direct fire. The AVRE reduced engineer casualties dramatically. Engineers still faced danger. Combat is inherently dangerous, but the ability to destroy fortifications from behind armour protection meant far fewer engineers died performing their mission. Exact figures are difficult to calculate, but post-war analysis estimated that AVRE deployment reduced Royal Engineer combat casualties by approximately 40 to 50% compared to what losses would have been using pre-AVRE tactics. Lieutenant John James Denovan, who'd survived Dieppe and whose observations had sparked the AVRE program, served as an engineering officer during the Normandy campaign. He witnessed AVREs in action on D-Day. His personal diary, preserved in the Canadian War Museum, includes an entry from June 7, 1944. Watched 77 squadrons AVREs clearing bunkers on Sword Beach yesterday. Every bunker they engaged was destroyed. Not one of my engineers died clearing those positions. At Dieppe, we lost 60 men trying to breach similar defences with hand-placed charges. The AVRE has vindicated everything we argued for. The weapon saves lives. Colonel Stewart Blacker never saw combat with his petard. By the time AVREs deployed to Normandy, he had retired from active service. But reports of the weapon's effectiveness reached him. He received numerous letters from AVRE crews, thanking him for creating a weapon that worked exactly as promised. One letter, from a bowgunner who'd survived the entire campaign from D-Day to Germany, stated simply, "Your spring never failed us. Not once. Thank you for keeping us alive." The technical achievement of the spring recoil system deserves recognition beyond its battlefield effectiveness. Blacker had solved a problem that conventional artillery engineers insisted was unsolvable. Mount a weapon generating 20 tons of recoil force in a tank turret using only a spring for recoil absorption. No hydraulics, no complex mechanisms. The solution was so simple that it seemed crude, but crude solutions that work are superior to elegant solutions that fail. The spring's durability proved that materials science in 1942 was more advanced than many engineers realized. The steel alloys available, properly treated and engineered, could handle stresses that theoretical calculations suggested were impossible. This lesson influenced post-war weapons development. Designers became less conservative in their estimates of what springs and mechanical systems could endure. If Blacker's spring could absorb 20 tons repeatedly, what else might be possible with proper engineering? The petard remained in British service until 1963. Post-war AVREs, built on the improved Churchill Mark VII chassis, continued using the same basic spring recoil system Blacker designed in 1942. 20 years of service without fundamental redesign is testament to how well the original engineering succeeded. Eventually, the petard was replaced by the L9A1 165mm demolition gun, which used conventional recoil mechanisms and could engage targets at longer range. But for the mission it was designed for, close-range fortification destruction, the petard remained effective throughout its service life. The spring itself became something of a legend among Royal Engineer units. New crews training on AVREs would be told the story of Hankley Common. The test everyone thought would fail. The spring that shouldn't work but did. It became a point of pride. We're the ones who used the impossible weapon. The spring that defeated Hitler's bunkers. May 1950, Korea. When North Korean T-34 tanks crossed the 38th parallel, British forces responded with Churchill tanks, some of which had been converted to AVRE configuration during the Second World War. The petard, designed to crack German bunkers in Normandy, found itself facing North Korean fortifications built with Soviet engineering expertise. The weapon performed identically to how it had 6 years earlier in Europe. Bunkers fell to single shots. The spring recoil system, now 8 years old on some vehicles, continued functioning without failure. British engineering officers, studying the Korean deployment, noted something remarkable in their reports. AVREs that had fired hundreds of rounds during World War II, been mothballed for 5 years, then reactivated for Korea, showed no degradation in the spring mechanism. The steel hadn't fatigued. The compression characteristics remained within original specifications. Springs that Blacker's critics had predicted would fail after a few dozen shots were still working after thousands of compression cycles. The Korean experience validated what AVRE crews had learned in Europe. Simple mechanical systems, properly engineered, are more reliable than complex ones. The spring had no seals to perish during storage, no fluids to freeze or degrade, no intricate parts to corrode. It was a coiled piece of steel. As long as the steel remained intact, the spring functioned. This reliability became the standard by which future weapons were judged. If it can't match the petard's spring for durability, the design needs reconsideration. The technical papers published about the petard recoil system after the war became required reading in engineering schools. The case study was perfect for teaching principles of mechanical design. Faced with a seemingly impossible requirement, 20 tons of recoil force in a confined space, Blacker rejected conventional wisdom and returned to first principles. What does a recoil system need to do? Absorb energy, release it controllably. How can that be achieved with minimum complexity? A spring. The solution was so obvious in retrospect that students wondered why it wasn't tried sooner. The answer, engineering professors explained, was that conventional artillery design had become dogmatic. Hydraulic recoil systems worked beautifully for their intended purpose. When you're designing a large artillery piece with plenty of space and weight allowance, hydraulics are ideal. But when constraints become severe, small space, lightweight, high reliability, dogmatic, adherence to conventional solutions fails. Blacker succeeded because he wasn't constrained by artillery orthodoxy. He looked at the problem fresh and chose the simplest solution that could work. This lesson influenced weapons development throughout the Cold War. When the United States developed the M40 recoilless rifle, designers debated complex mechanisms to manage the weapon's recoil. Someone referenced the petard spring system. Could a similar approach work here? Testing proved it could. The M40's recoil system incorporated mechanical springs as primary energy absorbers, reducing complexity and improving reliability. Soviet weapons designers studying captured AVREs after the war incorporated similar principles into their own engineering vehicles. The influence extended beyond military applications. Industrial equipment designers dealing with high-energy mechanical systems studied the petard spring. If a spring could absorb 20 tons of force in a tank turret, similar principles could apply to heavy machinery, industrial presses, and construction equipment. The mathematics of energy absorption through spring compression became better understood because Blacker had proven it worked at scales previously thought impossible. But the most significant legacy of the petard and its spring recoil system was doctrinal, not technical. The weapon proved that engineer operations could be conducted under armor protection with devastating effectiveness. This concept shaped how modern militaries approach obstacle breaching and fortification destruction. Today's combat engineer vehicles, whether British, American, German, or Russian, all descend conceptually from the AVRE. They're armoured. They carry specialised demolition systems. They're designed to operate in direct fire environments where unprotected engineers would be killed. The Israeli Defence Forces, studying British AVRE operations after World War II, developed their own combat engineer vehicles based on captured enemy tanks. The principle was identical: put engineers inside armour, give them weapons to destroy obstacles and fortifications remotely, protect them so they can do their jobs under fire. This doctrine proved critical in multiple Arab-Israeli conflicts, where fortifications and obstacles dominated the battlefield. Modern systems, like the US Army's assault breacher vehicle, based on the M1 Abrams tank chassis, are direct descendants of Blacker's concept. The weapons are different, line charges and plows instead of the petard, but the underlying philosophy remains unchanged. Engineers need armor protection to survive in combat. Give them a platform that can destroy obstacles, and they'll keep your forces moving forward. This is what Denovan realized watching his men die at Dieppe. This is what Blacker engineered into reality with his spring recoil petard. The Churchill AVRE appears in military museums across Britain and the Commonwealth. The Imperial War Museum in London displays one prominently in its World War II gallery. Visitors can see the stubby petard barrel, the modified turret, the side doors that engineers used. Tour guides explain how the weapon worked, how the spring absorbed recoil, how one tank could destroy bunkers that conventional weapons couldn't touch. Children listening to these explanations often ask the same question: why did they use a spring instead of something more complicated? The answer teaches an important lesson. Sometimes the simplest solution is the best solution. Engineers should be smart enough to recognize when complexity isn't necessary. The tank on display at the Imperial War Museum is T-68024B, nicknamed Bulldog. It served with 77 Assault Squadron, Royal Engineers, landing on Sword Beach on D-Day. The vehicle destroyed at least 12 German bunkers during the Normandy campaign, continued service through France and Belgium, and participated in the Rhine crossing in March 1945. After the war, it served as a memorial to 26 Armoured Engineer Squadron before being transferred to the museum in 2000. The spring inside its petard turret, original equipment from 1944, remains intact. Museum conservators examining Bulldog's recoil system in 2015 were astonished by its condition. After 71 years, including 5 years of combat service, the spring showed minimal wear. Metallurgical analysis confirmed the steel's properties remained within original specifications. The spring could still absorb 20 tons of force if called upon to do so. This durability, conservators noted, was exceptional for any mechanical component, much less one subjected to combat conditions. It spoke to the quality of British wartime manufacturing and the soundness of Blacker's original design. Stewart Blacker died on April 19th, 1964, age 76. His obituary in the Times of London mentioned his service in the Indian Army, his inventions including the Blacker bombard and PIAT anti-tank weapon, and his contribution to the petard mortar. But the obituary was brief, noting that Blacker had lived quietly after the war, maintaining a low profile. Most people reading it wouldn't have understood the significance of his work. They wouldn't have known that his spring recoil system had helped win the war. The Royal Commission on Awards to Inventors, the body responsible for compensating civilians whose inventions were used by the military during the war, awarded Blacker £25,000 for his contributions to the bombard, PIA, hedgehog anti-submarine mortar, and petard. In 2024 currency, adjusted for inflation, that's roughly £1.2 million. A substantial sum, but arguably insufficient for inventions that saved thousands of lives and contributed directly to Allied victory. Blacker never sought fame or recognition beyond fair compensation. He was an engineer and inventor driven by the desire to solve problems. The problem in 1942 was how to mount a massively powerful weapon in a tank turret without hydraulic recoil systems. He solved it with a spring. The solution worked. For Blacker, that was sufficient reward. The crews who operated AVREs during the war had a different perspective. To them, Blacker was the man who'd given them a weapon that never failed when they needed it most. The man whose spring had kept them alive through some of the most intense combat of the war. After-action reports from AVRE units consistently praised the weapon's reliability. We trusted it. It worked every time. That reliability came directly from Blacker's decision to use the simplest possible recoil mechanism. Veterans organisations in Britain maintained contact with Blacker after the war. He attended several reunions of 79 Armoured Division, where AVRE crews would seek him out to thank him personally. According to witnesses, these encounters visibly moved Blacker. He wasn't comfortable with praise, but hearing from men whose lives his invention had saved clearly meant something to him. One veteran recalled Blacker saying at a 1958 reunion, "I just did the mathematics and chose the simplest solution. You men did the hard part, driving into enemy fire. I'm honoured you found the weapon useful." This modesty was characteristic. Blacker could have promoted himself as the genius who'd solved an impossible problem. Instead, he deflected credit to the crews who used the weapon and the manufacturing workers who built it. "Engineering is a team effort," he would say. "I designed one component. Many people made it real." This attitude earned him respect among the engineering community, even as it kept him from wider public recognition. The physics of the petard spring recoil system have been analysed extensively in engineering literature. The key innovation wasn't the use of a spring per se. Springs had been used in recoil mechanisms before. The innovation was scaling the concept to handle forces that conventional wisdom said would destroy any spring. Blacker achieved this through three critical design choices. First, he used a steel alloy with exceptional elastic properties, capable of extreme compression without permanent deformation. Second, he engineered the spring's dimensions to allow compression over sufficient distance that force per unit area remained within tolerable limits. Third, he designed the mechanism so the spring's decompression automatically recocked the weapon, turning a potential weakness, violent spring expansion, into a functional advantage. The mathematics underlying these choices were straightforward. Energy equals force times distance. 20 tons of force over 2 feet of compression equals a specific amount of energy. If the spring steel can store and release that energy without exceeding its elastic limit, the system works. The challenge was manufacturing spring to exact specifications. Too much variation in the steel's properties or the spring's dimensions would cause failure. British manufacturing in 1942 rose to this challenge, producing springs that met Blacker's requirements with remarkable consistency. Post-war testing of springs removed from retired AVREs revealed manufacturing quality that impressed modern engineers. Tolerances were held to within thousandths of an inch. Heat treatment was uniform throughout the steel. Coil spacing was precise. This level of quality control, achieved without modern computer-controlled machinery, demonstrated the skill of British industrial workers during the war. They understood that their work directly affected whether soldiers lived or died. They built accordingly. The petard's operational history provides one of World War II's clearest examples of a weapon performing exactly as designed in every situation encountered. Some weapons looked good on paper but failed in combat. Some succeeded but revealed unforeseen limitations. The petard worked as promised from Hankley Common in May 1942 through the final days of the war in May 1945. Bunkers fell. Springs didn't break. Crews trusted it. This consistency, across 3 years of combat in multiple theatres, from Normandy beaches to German cities, validated every design decision Blacker made. Military historians analysing decisive weapons of World War II often focus on famous systems: the Sherman tank, the Spitfire, radar, the atomic bomb. The Churchill AVRE with its petard mortar rarely receives similar attention, perhaps because it was a specialist vehicle produced in relatively small numbers. 750 AVREs compared to tens of thousands of Shermans. But measured by impact relative to numbers produced, the AVRE ranks among the war's most effective weapons systems. Each AVRE destroyed multiple fortifications that would have cost dozens of lives to reduce by conventional time-served methods. Each one protected engineers who went on to clear obstacles, build bridges, and breach defences. Each one contributed directly to shortening the war. The spring recoil system's contribution to this effectiveness cannot be overstated. Without a reliable recoil mechanism, the petard would have been unusable. With Blacker's spring, it became a weapon crews could trust absolutely. In combat, trust is everything. A weapon that might fail creates hesitation. A weapon that works every time creates confidence. AVRE crews approached German bunkers with confidence because they knew the petard would fire, the spring would absorb the recoil, and the bunker would be destroyed. That confidence translated directly to tactical aggressiveness, which translated to faster advances, which shortened the war. The engineers who died at Dieppe in August 1942, men like Sergeant Roberts, who was cut down trying to place charges on a pillbox, didn't die in vain. Their sacrifice drove the development of the AVRE. The weapon that emerged from that disaster saved thousands of their successors from the same fate. This is how military innovation works in war. Failures identify problems. Engineers solve problems. Soldiers benefit. The cycle continues. But the human cost of each iteration is real. Real men dying because the right tool doesn't exist yet. Real families receiving telegrams. Real graves marked with crosses. The AVRE and its petard represented a rare achievement. A weapon developed quickly, deployed successfully, and performed reliably throughout its service life. No scandals about defective equipment, no cover-ups of failures, no controversies over whether it worked as advertised. Just a solid, dependable piece of engineering that did exactly what it was supposed to do. In an era where military procurement often produces troubled weapons programs, the AVRE's development and deployment serve as a model of how things should work. From concept in October 1942 to combat deployment on D-Day, June 1944, 20 months. Modern military development programs often take a decade or more to field a new weapon system. The AVRE went from drawing board to destroying German bunkers in less than 2 years. This speed was possible because the design was fundamentally simple. Convert existing Churchill tanks. Install Blacker's petard with its spring recoil system. Modify the interior for engineer equipment. Add side doors. Test it. Build it. Deploy it. No revolutionary new technologies. No years of experimentation, just practical engineering applied urgently to solve a critical problem. The urgency came from the calendar. Allied planners knew D-Day was coming. They knew the Atlantic Wall would be formidable. They knew engineers would need a better way to breach fortifications than running at them with satchel charges. The AVRE had to be ready in time. Delays meant more casualties on the beaches. This pressure focused everyone involved: designers, manufacturers, testing crews. Everyone understood the stakes. Your work will save lives or cost them. There is no middle ground. This clarity of purpose drove the project forward at remarkable speed. The spring recoil system, central to the weapon's success, emerged from the same urgency. Blacker couldn't spend years developing a perfect hydraulic system. He needed something that worked, could be manufactured quickly, and wouldn't fail in combat. A spring met all three requirements. It worked because the physics were sound. It could be manufactured quickly because British industry knew how to make springs. It wouldn't fail because properly designed springs are inherently reliable. The solution was obvious in retrospect, but it took Blacker's engineering insight to recognize it in the moment. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.